Hey guys, welcome back. We have integrated rate laws today. And so, what integrated rate laws do is we're going to look at how the concentration right varies or changes with time. Concentration with time. All right? And so if we had a reaction here, let's just say we had a reaction. H2O2, hydrogen peroxide in solution. You had that at home, and in the bottle at home, it's going to decompose to water and oxygen gas. And of course, there's coefficients here. All right, that's going to happen. All right, so there's an expiration date on hydrogen peroxide. It doesn't have the shelf life that you know, like sodium chloride, for example. Sodium chloride has a shelf life that it's good. This one does not. Okay, and so it has an expiration date. Now we know from the method of initial rates that K, the rate constant, let's just say at 25 degrees Celsius, is 1.8 times 10 negative 5. Second negative 1, and that's at 20 degrees Celsius. All right. Now, we know you bought your hydrogen peroxide bottle, you know, as it comes home, right? All right. As this reaction proceeds, all right, the concentration of reactants and products change. Right? And how does that work? It depends on the reaction order. So it depends on the order of the reaction. So let's just say we found out that this is a first order reaction. So we'll do first order as first order. First order first. So we're going to have concentration at H2O2 going to its products, right? Generically, concentration at A going to products. You'll see that. I'm going to use hydrogen peroxide because it's a real example. I like that better, but a lot of times you'll just see A, okay? So now we're going to have two things. We have the relative rate, all right? And these are the rates relative to each other. And then we're going to have the rate law. All right? So I'm just going to do, for the relative rate, all right, we're going to have the rate in purple would equal negative change in concentration of hydrogen peroxide, right, with the change in time. All right, because I'm just looking at hydrogen peroxide. I'm not going to compare it relative to the whole thing. I'm not doing the negative 1/2. I'm just going to do negative change in hydrogen peroxide with change in time as the rate. All right, so that's the relative rate of hydrogen peroxide decomposing. All right, the rate law, all right, would be the rate would equal the rate constant K, which we would get from experiment, times the concentration of hydrogen peroxide to the first power. Right? So that's the rate and the rate law. And what we're trying to do is we're going to try to figure out if I have concentration of hydrogen peroxide and time here. So this is my time. And this is our concentration of H2O2. it's going to start up here, right? And it's going to do something like this with time. We want to be able to figure this out, right? We want to be able to figure out, so at any time t, right? So if time, this is 0, obviously. Anytime t, so anywhere in here. Right here, I want to know what our concentration is. Right here, I want to know what our concentration is. So we need to build this line. Okay? We're going to build this line. Now, you might see the rate at this moment and the rate at this moment. These rates are the same. Right? So the rate will equal the rate, which is great. So that means the negative change in concentration of hydrogen peroxide, right, H2O2, the change in time, will equal K times concentration of hydrogen peroxide to the first power. Right, so that's what we have here. Now, I have concentration. That's a concentration of hydrogen peroxide, and that's a concentration of hydrogen peroxide, and they're on opposite sides. All right, so I'm going to separate. We're going to separate concentration. Actually, I'm not going to separate. We're going to combine. Sorry, separate concentration. Yeah, I'm going to separate concentration and time. So I'm going to combine the concentrations. All right. So that means I have to multiply both sides by the change in time and divide by the concentration. So I got to multiply by delta T here. All right. And so if we do that, we get negative change in concentration of hydrogen peroxide, H2O2. Right, equals K times the concentration of hydrogen peroxide times the change in time. Now, what I should have done is made this multiplied by the -1 as well. We'll do that later, though. All right, now we're going to divide by our concentration of H2O2. All right, so doing this, we get negative the change in concentration of hydrogen peroxide all over the hydrogen peroxide concentration. So H2O2, K delta T. Now, I technically want to do that. Can we do that? I multiply both sides by -1. All right? So I'm going to write that here. And multiply both sides by -1. All right, so now I have concentration and I have time. Concentration on the left, time on the right. Now, you might see this, right? You might have seen this before, something like 1 over x dx equals -k dt. You might have seen that before. Maybe you have, maybe you haven't. All right? And so, what are we doing here? I'm going to do something called integration. All right? Again, if you've never seen this before, that's okay. We're just going to give you the result. You're not going to actually have to do this process in this course, but we're going to give you the result. Okay? What we're going to do, all right, is you're going to have your concentration, your change in your concentration of hydrogen peroxide, over the initial, or over the concentration of hydrogen peroxide, equal to negative K change in time. So what we're going to do here is this thing called integration, where this is a big fancy S, right? And constants come outside of the integral. And so we're going to integrate, all right, from the concentration of hydrogen peroxide at time 0 to the concentration of hydrogen peroxide, or A, whatever it is, at time t, from t equals 0 to time t, whatever that time is. All right. Okay, so that we're going to figure out this curve. All right, we're figuring out this curve right here from time 0, which is right here is time 0, to whatever time t is. Well, so we're going to build the whole curve because t can be, any time. And so if we do this math, all right, all right, you get the natural log of the concentration of hydrogen peroxide, or A, or whatever we're talking about, first order, at time t, all right, minus the natural log of the concentration of hydrogen peroxide at time 0, right, equal to negative K T. That is your first order integrated rate law. So a lot of times you'll see it this way, all right? Two forms. So you'll see the natural log concentration, that would be A at time t, over concentration at A at time 0. That's all in the natural log, equals negative K T. Right? So, because remember, log of hydrogen peroxide here, this log of hydrogen peroxide here, minus this log of hydrogen peroxide here, right? It's the same thing as dividing them, if you remember that. So that is one form of the equation. The other form would be the E form, where we do natural log to both sides. All right? And a lot of times you'll see it this way. If I do that, you'd get the concentration at A times T over concentration at A at time 0 equals e to the negative KT. So a lot of times you'll see it this way, where you have that concentration at A at time T equals the original concentration, e to the negative KT. All right, so those are the two forms we'll have. All right, and so you don't have to know the calculus. Like, you'd have to memorize this integral, and that's fun. Maybe you're in calculus and you've done it. Maybe you've never done calculus, and that's fine. But that's what we get. Okay, and so we're going to get this as an equation that we care about, and this. All right, and so as you can probably tell, all right, depends on what you're solving for. If you want to solve for K or you solve for T, you're going to use this form. If you want to find the concentration at any given time, you're going to use the E form. All right. Okay, so that is the first order integrated rate law. Now, another concept that comes in here a lot is half-life. Half-life. All right, what is half-life? So half-life, this is the time required for half, right, of the, time required for half to react, right? But time required for the concentration of whatever reactant, any reactant, to fall to 1/2 of its original value. All right, so use half of it, which is kind of weird. All right, because it doesn't matter in this case, it doesn't matter the amount. Let's dive into this. All right, So if I have the concentration of A at time t would be 1. And the concentration of A at time 0, 2, right? So if I start off with 2 moles. And at half-life, I would have 1 mole left, right? And so let's look at this. If we do this, right, the natural log of concentration A at time t minus the natural log of concentration of A times 0 equals negative kT. Well, we know this is 1, that is 2. So the natural log of 1 minus the natural log of 2 equals negative kT. All right. Well, if you do in your calculator, natural log of 1, that's 0. So I get negative natural log of 2 equals negative kT. Well, I want t by itself. All right, so I divide both sides by negative k. So that means I get natural log of 2 divided by k equal to t. So t1/2 is the natural log of 2 divided by k. So that is the first order half-life formula. So it doesn't matter how much we start with, right? If you start with 100 grams of something, after a half-life, it's down to 50 grams. Which is weird to me, right? Because, I mean, think about this. If I start with 100 grams, 1 half-life would be 50 grams. 2 half-lives, 25 grams. And you guys can keep going, right? If you start with 10,000 grams, 1 half-life would be 5,000 grams, right? It's the same thing. And so you can have the same substance, right? Doesn't matter what the substance is, but that's just what half-life does, which is crazy to me, but that's what it works. All right? So that's first order half-life. Now, there's 2 more we're going to do. All right? There's 2 more. And we're going to kind of go quickly with this. We're going to have second order reactions, and I'm going to have 0 order. So second order reactions, A yields products. All right. And with this, we know that our rate law would equal K times the concentration of A to the second power. And the relative rate would equal the negative change in concentration of A with the change in time. All right, so we're going to set those equal to each other. Negative change in concentration of A with the change in time equals negative, equals positive Ka squared. Yes, let's don't get ahead of myself here. A dt All right, we gotta switch this around a little bit. All right, so we'll get negative change in concentration of A over concentration of A squared equals negative K dt. Right, just like we did with first order, we separated the concentration and the time. All right? And then we do calculus again. We're going to do the same integration from the original concentration, right, to whatever the concentration is at time t, and from time 0 to time t. All right? Okay? And this is 1 over x squared dx. And if you do this, right, with calculus, you get 1. No, I'm in green. Let's try that with green. 1 over the concentration of A, whatever it is, whatever A is, at time t, equals KT plus 1 over the original concentration of A. So there is your formula for second order integrated rate law. And then the half-life, T1/2, is equal to 1 over K, the rate constant K, times the original concentration of A. All right? Which means it's different now. If we look at first order again, right here, our first order half-life, it is the same, because natural log of 2 doesn't change. 0.0 is like 693, or 0.693, whatever natural log of 2 is. And then K is whatever the rate constant is. That is a number, and that number is not changing. Second order, that's on the bottom. So if we go from 100, 1 over 100 is a small number, over 1 over 50, that's not as small as a number. So each half-life for second order is twice as fast, which is kind of neat. All right, zero order, same, we're going to do this one now. Still have an A going to products. All right, and we're going to have our rate. Rate law is rate equals your rate constant K. And it's just that, because technically it's concentration A to the 0 power. So all that's gone. So the rate is just K, right? Rate is just equal to K. The relative rate, though, however, is still negative change in concentration of A with the change in time. So do this again, all right? You have negative change in concentration of A with the change in time. Just equals K. And so that means, oh, I made a mistake here. That's positive now, isn't it? The change in concentration of A, right, equals negative K. Oh, wrong colors. All right, so if we get our integration done, right, which we don't know have to know, concentration at A at time t, right, equals negative K, rate constant K, times the time, plus the original concentration of A, whatever A is. All right, and then finally, zero order half-life, T1/2 will equal the original concentration all over 2K. So these are our formulas. There's 1, So those are our second order and zero order. So now we have all of our integrated rate laws. And what we're doing is we're figuring out the curve so we can actually figure out how much of each of these reactants are left, right, at any given time. All right, so if you start off with hydrogen peroxide at home and you know the rate constant, you know what temperature has been at, and if it's been at a consistent temperature, there's some factors there, you can figure out how much is left. All right, it's kind of neat. Not that you would do that, you're probably just going to look at the expiration date, and some of you, the expiration date's very important. And, oh, it expired last week, we're going to get rid of it. And some of you think expiration dates are a waste of ink, and you just keep on using things. But either way, that's integrated rate laws. Hope that makes sense. If you have any questions, let me know. And in the next one, we'll do some examples. Take care, guys.